All right, thank you, everyone. Oh, wow. So, um, I'm going to try. Well, I mean, this is a big question. How does gradient descent find a good minima instead of previous one? I'm not going to answer this. I will try to say something about it. Also, the point of view I took for this talk is I was speaking just after two of my collaborators, Giulio Biroli and Lenka Zdeborova, who gave kind of a bird view of what we have been doing as a community in this problem, and each of them tried to give a very high level highlight of the activity of the field. So I will try to do something else, okay, since I'm the third speaker, and I will try to show you one precise work. And so I choose one thing that we have done, the three of us, and it's about trying to answer this question, right? Okay, so this is a pretty big question. We heard about optimization problems in the first day by Natis Brero. And the question is the following. So we have all these high-dimensional non-convex learning problems, and it works, right? You just do gradient descent, and often it works. Sometimes it doesn't, but very often it works. And so the question is, why does it work so well in practice many times? And in practice, what you want to care is, how does energy in the loss landscape affect behavior of gradient descent algorithm, right? We have this idea that when there are many minima, it's hopeless. And so is it true? Is it true that when we have many spurious minima with have high values and are not correlated with anything, is it really hopeless? And it should not be, because otherwise things will not work. So there are many answers to this that you find in the literature. One answer that you find often is the following one. If you have enough data, or if the noise is small enough, or if you want, as a signal processing person, you would say the signal to noise ratio is high enough, you hear that all minima are actually good. That's a situation that actually has been investigated by many people. There's a large body of works in mathematics, in CS, and stat in this direction. I'm giving an example here in community detection. For instance, you can show this. This is true. If you have large enough SNR, then all minimas are good. There are many of them, but they are all good. Let me say, they are maybe not all good, but none of them are really bad. You can see this in matrix completion problem, tensor factorization, and there are some works showing that this is the case also in overparameterized neural nets. It's actually probably why you want them overparameterized, to avoid these spurious minima. The point is, if you dig into these works and if you look at the numerical evidence, you see that it cannot be the only side of the story. Because when you do simulation, in many of these situations, you see that things work, even though they are very far from what people can prove. They say, oh, with their large SNR, we have no bad minima. And then we do simulation, and it works at lower SNR. So maybe this is not everything. So maybe something else must be going on. Okay, so this is what we try to investigate. And so what did we need for this? Well, we needed to have one case which we could analyze, in which we could compute, what are the optimal performance, what's the kind of best learning you can do. Then, of course, you need to be able to analyze gradient descent, because that's what we're interested in. And if you want to compare and to understand the properties of gradient descent with respect to the landscape, you need to be able to analyze the landscape. So we needed all these ingredients. And we did some brainstorming with Giulio and Lenka and our students. And we were not very original. We looked at one of the most beloved model in statistical physics, at least for people doing spin glasses, and it's called the spiked matrox tensor model. So this is very far from deep learning, all right? But it's a very simple model on which we can do everything, and let's try to see what is going on. Okay, so that's what we did. All right, what is it? So this is what it is, all right? So you have a signal. If you want, you have a vector, x star, which is in Rn, and you don't know it. But you are, someone is giving you some information. So I'm giving you two things. One, I'm giving you a matrix, which is Yij, which is here, right? Well, I will do it here. And Yij is just xi is j. You divide it by square root of n to make it small. And I'm adding a noise with a given variance, right? And since I'm a nice person, I'm not giving you only this one. I'm giving you also an object with p indices. In fact, I will take p equals 3, so think about 3. T, ai, I1, I2, I3, which is xi1, xi2, xi3 plus some noise. Okay? And in fact, what it means is that I'm giving you a matrix, which is a rank 1 matrix plus noise, and a tensor, which is a rank 1 tensor, order p, so in this case 3, plus noise, right? So I'm giving you a noisy observation of S vector. And the rule of the game is, well, if I'm giving you y and t, this matrix and this tensor, can you find back x? All right? So clear that it depends on the intensity of the noise. For instance, if delta 2 is 0, it's totally trivial, because this is a rank 1 matrix. We'll just look at the eigenvalue decomposition of S guy. It will have only one non-zero eigenvalue. You look at the eigenvector, and it gives you x up to a plus or minus 1 shift, right? So in that case, it's easy. And if delta 2 is infinity, well, there is no way you cannot do anything, right? So now I have two different noise, and it's interesting. So what do we know about this problem? All right, so before talking about algorithm, let's try to see what do we know, and when it's actually something we can learn or not. So it turns out we know a lot. We even have rigorous theorems about it, which I will state informally. So if you are a physicist, what you want to compute all the time is the log of z, when z is a normalization of something. Anyway, the point is there is this object here, which is called the free energy or the mutual information, if you want. And what we can show is that the mutual information between what you observe, matrix and the tensor, and the unknown, which is a vector, is given by the maximum of this function. Okay? Very simple function. This in the limit of very large dimension. And why is this interesting? Maybe you don't care about this thing, and you are right. It's interesting because once you do this maximization, okay, it's maximized for a value m star, and this value m star is giving you the best possible reconstruction you can do in this problem. Okay, so the theorem is that the best means reconstruction you can get in the sense that it achieves a minimal mean square error. Okay, so square difference between the truth and your estimate is given by 1 minus m star. Okay, so if m star is 0, if your delta 2 and your delta p is such that that is maximized in 0, that means that the best possible error you can get is 1, which is what you will get with a random guess. So it means in that case, you cannot beat a random guess. If it's something else, then you can hope to learn something about this hidden vector. All right, so this is a nice result, which was obtained with statistical physics techniques and then proven with mathematical physics techniques. But it's maybe a bit abstract here. Let's see what it actually means. This is what it means. If you do a phase diagram, which is what we like to do in physics, so here you have 1 over the noise on the matrix. So if you want, this is the SNR on the matrix. And here I'm putting the noise on the tensor, or 1 over the SNR. I'm sorry, but this is a nice way to plot it. This is what you get. So with this whole region here, where indeed my function is maximized when m star is 0, and this means there is no way I'm going to learn anything. Okay? And it's, even if you use billions of GPU, you cannot learn. Okay? There is just no information in the vector, in the matrix. Sorry, in the matrix, in the tensor. There's not enough information to say anything about the hidden vector, right? And now you have these lines here, which actually goes up to this point, which is 1, 1. In all this region, we know that some inference is possible. Okay? You can get something, and if you go in this direction, then you go to toward the perfect reconstruction. Right? So we have this region where we know it's theoretically possible to learn something. Another question is, fine, now what about algorithm in practice? Okay, and we have been working a lot in this, and we try to invent very smart algorithm. Not that smart, but specially designed algorithm. We try to be really smart and to try to see if we can actually learn this vector in polynomial time, and we know to do it. In fact, there is this whole region here, up there, which is lambda 2 larger than 1, in which we have polynomial algorithm which can provably find the best possible representation of the vector. Okay? And now you recognize something that Lenka discussed. You have this easy region where we have good algorithm. You have the impossible region, and now I left this guy here. Very interesting region in which we know it should be theoretically possible to learn the vector. In fact, if you give me billions of GPU, I will do it. I just have to do a Monte Carlo simulation and run it a long time, but I don't know any good algorithm to do it in polynomial time. Okay, this is this hard, easy, and impossible region that Lenka mentioned, and also Giulio. Okay, so I really love this subject. This is not what I want to discuss today, because what I want to discuss is what happens if you don't try to be that smart. Okay, and in practice, no one wants to be smart. No one wants to really think hard about a particular algorithm for a task. You want to take an off-the-shelf solution. And in that case, what you want to do here is to write a cost function and do gradient descent. Or maybe this is not what you want to do. This is what most people want to do. And it's a very good strategy, as we have learned. So the question is, what can you do with gradient descent for this problem? Okay, when does it work? When is it optimizing something? And can we try to connect it with landscapes? Okay, let's do this. So what does it mean, gradient descent? Well, here it's very easy. You just write the maximum likelihood, and it's trivial to write. I mean, essentially, you want your x that minimize the L2, oh, that's not the L2, it's probably the Frobenius norm here, sorry. But the square difference between y and x transpose, and the square difference between the observed tensors and x to the tensorial product to the 3, right? That's exactly what the cost function is. This is how data were produced, so that's what you should minimize. So what you should do is to write down this cost function and do a gradient descent. In fact, I also know that my vector is normalized to n. So one thing you might want to do is to write this constraint here. And this is why the problem is called the spherical problem. This means that x is on the sphere. Now, it turns out that we know a lot about this problem, because if you write what it is, it's something that people call the Spingler's problem. It's a p-spin problem. It's a 2 plus p-spin problem. This is a Hamiltonian that corresponds to this problem. And there have been a lot of work about this problem in physics. So we are just borrowing the technology, and this is the kind of thing that Giulio was mentioning this morning. So how do we analyze gradient descent here? The point is there are lots of work. There is a large body of work on the Langevin algorithm for this problem. So the Langevin algorithm is written like this. You want to have each of your components of your vector, and you are doing something which is very close to a gradient descent. You have your spherical constraint, and on top of this, you have a noise. You have a small random noise. Okay? Gradient descent will be just the 0 temperature limit that you get here. Well, not quite, because this is in continuous time, so this is more gradient flow. So we are not actually studying gradient descent here. We are more studying gradient flow, because this is what we can do. All right, so that's the kind of thing that we would like to do. Now, how to analyze the behavior of gradient descent here? Can we do it? And it turns out that it was done for us in the community quite some time ago. Giulio mentioned that it dates back to some amazing work by Sompolinsky and Zipelius. For that kind of problem, in fact, was adapted in a very famous paper in physics by Letizia Cugliondolio and Jorge Kirchner in '93. And they actually, the title says it all, analytical solution to the dynamics. So just tell you what the dynamics is doing. Same year, there is a similar paper by the Roman team. And in fact, life is really well made, because we even have proof that these equations are correct. Okay? We know that what is described in this paper is a correct and rigorous description of the dynamics going on in these systems. And this is due to work by Gérard, Mirdambo, and Alice Guyonnet. So what we did was to generalize this work in the slightly different case, which is the one when we have a spike. Right? The difference between our work and those works, in that in this case, the y and the t were entirely random. Right? Here we have a spike. They are not entirely random. They contain some information about a hidden vector. And so it's a bit of, you have to adapt it, but it's not so much work. And okay, so there's a long computation, and this is what you get at the end. You can entirely describe the behavior of gradient descent in this problem with PDEs. And the PDEs are a closed set of equations on these quantities. So this is the correlation between the state of the system at t and t prime. Physics love to study this. This is something that we look as a correlation in time to see the system in aging. This is called the response function. And what is really important for us is this guy, because this is the correlation between the state of your system at this time and the hidden vector, the x star, right? So if this guy is positive, it means you start to correlate with the hidden assignment. All right, so the equations are not so nice. I mean, not scary, but clearly you cannot just plug this in Mathematica and hope that you can integrate this. So you have to work a bit, but we have good students and people in statistical physics and the theory of the glass transition looked at these equations for a while, so we know how to do it. So we took this, put it in a computer, and let's try to see when the gradient descents actually find something correlated with the minima, with the spike, the Gaussian vector. All right, so this is the result of the numerical integration. We found that there is this region here where gradient descent just work. Find something with a very good correlation with X star, and below this region doesn't work. It gets stuck in spurious minima forever. Okay, so we are very happy. And that's the result of numerical simulations, right? And you have these points. So after a while, we thought, okay, that's a bit too bad, because if it is just the result of numerical simulation, maybe we should just have done a simulation of a large system. So we looked at the equation and we tried to see if we could actually get an analytic estimation of the long time performance. And we did. This is what we get. We have an analytical line. I'm not showing you the expression, but goes through all these points. Okay, so this is very nice. We can say very precisely what gradient descent goes at very long time here. Fair enough. So what? Well, right now, it's not much informative. Yeah, it works here. It doesn't work there. It's not as good as a super clever algorithm, but that is to be expected. I mean, what's the point of being super clever if you are beaten by off-the-shelf algorithm? So let's try to see why it's doing this. That's a real reason, right? I mean, why do we observe this? So we turned to landscape analysis, and that's the second tool that was mentioned by Giulio this morning. All right, so let's come back. So we have this maximum likelihood estimator, and this is what it did, right? We need to minimize this guy. So the question is, can we compute the property of the energy landscape, of the Coates landscape, if you want? And that means computing the number of minima, number of saddle, at each energy level. And are there actually spurious minima, or only good ones? All these questions are the one we would like to answer. So as Giulio said this morning, there is a tool which is made exactly for this. It's actually quite an old object in mathematics, but that was used before at in low dimension. It's really thanks to the work of Fyodorov and Gerard and collaborator that it was brought to the realm of high-dimensional statistics, and it's called the Katz-Rice formula. Okay, the Katz-Rice formula is an object, as Giulio told you, that is telling you something like this. If you want to compute the log of the average number of saddle point, or let's say of critical point, for a given overlap M with a hidden solution, well, given by this object, which is, okay, kind of an ugly thing to compute. I mean, it's an integral in n dimensions, so it turns out looks pretty hopeless. But as Giulio told you this morning, there is a map from this object to random matrix theory, and if you work really, really hard, you can actually compute this number. And this is what happened if you do it. For this problem, it was first done by Gérard Benarous, Song Mei, Andrea Montanari, and Nika. Actually, they did it for the problem where you observe only the tensor. Okay? So in this recent work, we just add analysis when you observe also the matrix. It's not very different. It's just rank 1 perturbation. And so you have this ugly formula, which I'm just showing you the formula to show off. It's not particularly instructive like this. What is actually going on? All right, this is what is going on. So if the SNR is very small, this is what is going on. If you go at high energy, you have many saddle points. So you have a lot of critical points, but they have many negative directions. So they are not really at minimum. Okay? So if you go there, then you will escape because you have most of the direction are actually negative slope. And at some point, you are trapped into minima. So that means when you go down in energy, the number of negative direction is decaying, and at some point you reach real minima. So what do you expect? Well, if you are doing a gradient descent algorithm, it should go like this and stop here. And this is exactly what is going on. Okay? If you do a simulation at very low SNR, this is exactly what you observe. In fact, that is something which is classical in statistical physics. And there was simulations done by NYU team with Facebook team by Romanska, Gérard Benarous, Lequin, and others, who saw exactly this when you're in simulations. That's a paper from 2014. But they did it in a problem without the spike. Right? Now the difference when you have a spike is that maybe you have another minima deep somewhere, which is good. There is this guy who has a good overlap. The blue guy has a good overlap with the hidden vector. All these guys are spurious. Okay? If you are stuck here, you have no overlap whatsoever with the hidden vector. All right, so this is situation as low SNR. What happens when you increase the SNR? This is what is going on. This is a result of Krzakala's analysis. Well, what you see is that all those maxima died. You increase the SNR, or you reduce the noise, and then they die. Then you increase it again, some of them die, they die, and at some point, you have only one minima, and it's a good one. It's the one which has the best correlation possible with the hidden assignment. So when this happens, this can be computed, it's called the trivialization. This is the moment where, all right, there is no more spurious minima. All right, let's plot when this is happening. This is here. All right, this is a trivialization line. And now we see that our algorithm, which is gradient descent, is going, well, way past the trivialization line. So that means it's, gradient descent do not care about it. It works here, even though we have exponentially many minima. So it's an exact realization of what I was saying in slide 2. All right, this is nice, but why is it doing it? Okay, well, I mean, that sounds crazy. We have exponentially many minima, and there is one good one, and gradient descent find this guy. So we came back to the landscape analysis, and it turns out that the trick, if you want to understand this, and the whole talk is leading to this pun, okay, is you have to care about the fate of the spurious. Great movie. The point is, here I'm just showing you the minima. But those guys did not disappear. What really happens is this. These minima, when I increase the SNR, will turn into saddles. So they start to develop one negative direction at some point into the direction of the spike. And when I increase the SNR, what we see from the Krzakala's analysis is that, well, not only those guys that were minima here now have a negative direction, but those guys start to have a negative direction. And when you increase the SNR, you go deeper and deeper, and all of these guys start to have negative direction that goes in the right direction. Okay, so people that were minima start to develop a negative direction in direction of the spike. So let's change everything. Because now if I go back to my analogy, well, I'm going here, I'm not stuck here anymore, and I'm not going here because the only direction that I have is pushing me to the other direction. So it's like you go to the slope, and at some point you should go here, in the direction of all these bad minima, but you have this one negative direction that pushes you on the left. So you go on the left, and boom, you arrive to the real minima. And so that means that you go here, and you never saw all this guy. And it's interesting, because if I try to help you by giving you a good initial condition, look, you don't start up there, start here. And then you will be stuck forever, which I think is interesting. All right, so if this is true, we can try to compute this line when the maxima starts to fill for the first time the negative direction. And so this is what we did, and this was the trivialization line, and this is the fate of the spurious line, and you see that it goes perfectly with what we got. So I think I'm almost at the end, and in a nutshell, if I want to summarize what we have done, this is a simulation in which you will see here, it's not a simulation actually, it's the integration of numerical equation. Well, you see that I'm plotting the overlap with the hidden assignment. So it's 0 for a very long time. And okay, let's come back to the beginning. You see, when I start, most of my and this is the density of negative of the eigenvalue of the Hn or where I start. Right? And you see here I have a lot of negative direction. And sorry. When you do the simulation, you see that, well, I go down all these saddles, I have a lot of negative direction, and I go slower and slower and slower. And at some point I start to have less and less direction. In fact, I would have to zoom in here to see that I have less and less directions negative. In fact, the dynamics is slowing down, so I'm speeding it up. And at some point, there's one spike here, this one guy is becoming the only negative direction, and this is basically now. And when this is happening, I start to develop a correlation with the hidden direction. So this is showing now it's negative, and it's clearly the only guy, and I start to correlate with the hidden planted assignment. So this is an exact realization of the scenario that we observe. All right, so I think this is cute because this is one case where we actually understand what is going on. And okay, one question is it relevant at all? Which is not clear, of course. Maybe it has nothing to do with the truth that is going on in many interesting models, but at least we see why in this case you don't care that there are so many exponential minima, right? This is not what matters. What matters is actually what you do in the phase space. So to finish, we'll try to list some open problems. So there are many. I think this is just a starting point where we are trying to apply these techniques to learning problems. So of course, we would like to apply this to model of neural networks, single layer, multi-layer, that kind of the teacher-student that Lenka was advocating. Of course, what is really interesting is not what happened with these random models, but when you try to have something that mimic structure of real data and the presence of symmetry, and that's also something that we should look at. And also the dynamics is more interesting stuff like autoencoders and GAN. And of course, it's not only the structure of the data, the architecture also, which would be interesting. So can we try to repeat this thing in more complicated models? And another question is, well, that was for gradient flow, but of course, LGD is interesting. Can we say something about LGD algorithm with momentum, and try to study this precisely? And it's, I think, a very nice test bed for starting all this direction. All right, I think I'm 25 minutes, so I will stop here. Thank you. Yes. Which one? This guy. Sorry. There was no question yet, I think.
Um, can you give me again the intuition on? It seems that on the x-axis, right? To the right we have more noise.
Yes.
Here it seems to suggest that the more noise in the tensor, the better, the easier for the algorithm, right? What is your rationale, and what is because the reasoning would be maybe the opposite, right?
Yes. In fact, you see that if I use clever algorithm,
yes,
I find all this. So the problem here is the following. You think that the tensor is useful, and it's not. If you will be just throwing away the tensor data and use only the matrix, you will have a perfectly correct algorithm. You have a convex problem, and it's fine. Right? You don't find the best overlap you can because you are not exploiting all the information. But the trouble is that information theoretically, the tensor is giving you a lot more information, but it's really something super giggling with a lot of minima. And so the thing is that when you include the tensor, you are complexifying this landscape, and it makes things really harder. So I'm a bit cheating here, because if you are clever, what you will do is to say, haha, I will just use the matrix, minimize the matrix problem, and use this as a starting point. And this will be just fine, right? So that's one of the weak points of this model. It's extremely artificial. So that is true.
But somehow
at the same time,
if you noise into the tensor.
Yes, because if the tensor is very noisy, it's not trying to give you too much information. I don't have any. But think about it. You have something like this, and what is behind me? Well, I don't need a pointer. You just want to wave my hand. Yeah, that's good. All right. So one problem with a cross function like this. Then you have the tensor, and the tensor is containing a lot of information. Okay, but the noise is small. The tensor is something like this. So you have these two. This guy is actually perturbing me. When the tensor is very noisy, somehow it's not anymore that.
analysis without the tensor and you use this first result as an initial condition, won't you be stuck in spurious minima, as you said?
Depends what you call spurious. But if you do this, you can probably get something which is better than random. That's the best way to solve this problem, basically. Yes. Yes. So the obvious candidate is a number of data. And it's something that you actually see, at least, it's a simplified version that we see. If you take the SNR as a number of observations, number of data, you see that at some point, if you have enough data, everything is easy and you flow and you find a good guy. Otherwise, you are stuck in regions which are not optimal. And so, yeah, we'd like to think about the SNR as a mix between the complexity of the data and the number of data with respect to yes. Yes, that's probably true, actually. I mean, that's one of the school of some of people are doing this, trying to compute, if I have something which is over-parameterized. In fact, you can find paper like this. You have a two-layer problem, and the title will be two-layer network are easy. And then you read the theorem. Well, let's take a two-layer network with a number of data larger than the number of atoms of the universe, and then it's easy. Okay? And I think that the problem is that they are trying really hard to go in this region where everything is easy because you have only one minima or no spurious minima. And at least what we learn here, I admit it's a very simple problem, that you don't need that much. Okay? You can have nice conspiration of the landscape that help you a lot. And the reason why it helps you is that the negative direction appears first up. Is the guy up there that starts to give you information. That could have been the opposite, I didn't know, right? It could have been the bottom guy that starts to develop the negative direction. But no, it starts up there and it goes down. So it's going in a good direction. Now, the relevance of that scenario to what we see in neural net, okay, of course. An open question.
Skiing landscape happens with real networks?
Very good question. So I hope so. It's not exactly clear what to look at, but one thing that was looked at by a few years ago by Surya Ganguly, I think, with Yoshua Benjo, and also, but maybe there was a paper by Shonolds at Google. They started to look when you go down in some actual network with actual data. I don't know, G16 and Cypher 10, anything like this. And they started to look at when you goes down, how many negative direction you find with respect to energy. And they found things that look a lot what you have in spin glasses. So, there are some kind of evidence that suggests that that kind of energy landscape is not totally crazy and it might be, I'm using conditional, it might be relevant to some of the things observed. But yes, I think one could try to test these ideas. Of course, it's a lot of work, right? Because you have to gradient stop and start to evaluate the direction around you all the time. And so that's
not that familiar with the techniques, but is it possible to compute the Hessian and evaluate those negative
numerically?
Yeah.
Compute
them.
Okay. So this is exactly what this is. This is the Hessian.
You're computing the...
It was computed, yes. So in the large n limit, when n is infinity, this is exactly what we can do.
You can actually compute.
Yes. In this model.
Right.
But yes.